Hello, I'm Michikazu Hirata. Today, we will talk about program logic for higher order probabilistic programs in Isabelle HOL. First, we will explain about probabilistic programming languages. In probabilistic programming languages, programmers write a probabilistic distribution as a program, and the language supports sampling and conditioning. For example, let's think the distribution when we roll 2 dice and at least one die is 4. We can write this distribution in WebPPL as the function roll. It first generates 2 random integers from 1 to 6. Then we specify the condition that at least one die is 4 by the condition command. And finally, it returns the sum of the two values. This histogram shows the distribution. The least value is 5 because in the distribution at least one die is 4. The difference between normal programming languages and probabilistic programming languages is that probabilistic programming languages support not only sampling but also conditioning. Next, let's see more interesting example, the Monte Carlo method. It computes an approximation of the expected value. For a sequence x1 to xn sampled from a distribution D, the approximation of the expected value of h of x is the average of h of x1 to h of xn, where D is a probability distribution on x and h is a real-valued function from x. Here is the program Monte Carlo. It receives a sample size n and returns a probability distribution on real numbers. The program computes the average of h of x1 to h of xn recursively. Note that this program is higher order with respect to the function h. We expect the property that the greater n is, the closer Monte Carlo n is to the expected value. We will prove this property later. The standard semantics of probabilistic programming languages is based on measure theory. Probabilistic computations are captured by the probability monad, called the Giry monad G. In the semantics, programs are interpreted as measurable functions from its context to its type. If we want to apply this semantics to higher order languages, there is a critical problem. Function spaces with desired properties do not exist in general. In the previous work, Hunen and others introduced the notion of quasi-Borel spaces. The theory of quasi-Borel spaces provides a suitable denotational model for higher order languages. Because function spaces exist, and every probability distribution on standard Borel spaces is represented as a probability distribution on a quasi-Borel space. There is a restriction about standard Borel spaces, but many practical spaces, such as a countable product of real numbers and natural numbers and finite discrete spaces are included in the class of standard Borel spaces. And the probability monad is commutative strong. It is important for the semantics of the language. In order to verify probabilistic programs, Sato and others introduced the system PPV. PPV is a verification framework for higher-order probabilistic programming language. It consists of the language and three kinds of logics. And the language supports sampling and conditioning. And its semantics is based on quasi-Borel spaces. PPV is applied to verify, for example, properties of Monte Carlo method, importance sampling, and Gaussian mean learning. Our goal is verification of higher-order probabilistic programs with proof assistant. Our contributions are: first, we have formalized quasi-Borel spaces in Isabelle HOL. The second, we have formalized a core part of PPV, the language and two kinds of logics. There are some differences between our PPV and the original PPV. Our PPV does not support conditioning, and we introduced the notion of integrability in the logic because it is necessary. And finally, we verify the Monte Carlo method on our mechanized PPV, including the integrability of the program. We choose the proof assistant Isabelle HOL because it has a rich probability theory library, including the Giry monad. Our formalization consists of around 12,500 lines. Today, we will talk about verification of Monte Carlo approximation and the formalization of PPV. This is the Monte Carlo method and the program we showed in the introduction. It computes the approximation of the expected value. And the approximation is the average of h of x1 to h of xn. The program Monte Carlo has the famous property, the weak law of large numbers. The theorem says that the distribution of the average converges in probability towards their expectation. We will prove this property formally in PPV. The judgment as the third line corresponds to the weak law of large numbers. The judgment is a UPL judgment, one of the logic of the PPV. In the judgment, the gamma is the typing context. Now, epsilon, mu, and sigma are real numbers, and D is a probability distribution on X, and H is a real valued function from X. And C is a set of assumptions. We assume that the square of sigma is the variance of H, and mu is the expected value of H, and epsilon is positive, and integrability. The predicate integrable has the same meaning of the mathematical integrability. That is, integrable mu f means that the expected value of f exists as a finite value. F is integrable with respect to mu. And this part is the program and its type, and the last statement is the conclusion. The variable r in the conclusion refers to the program, and hence the probability in the conclusion corresponds to the probability in the weak law of large numbers. From the inequality in the conclusion, the probability converges to 0 as n grows larger. In addition to the weak law of large numbers, we show the integrability of program. The judgment at fourth line is a PL judgment, one of the logics of PPV. It consists of the typing context and the set of assumptions and conclusion. This judgment means that the expected value and the variance of the program Monte Carlo exist as finite values. We proved this integrability because it is required to prove the UPL judgment, the weak law of large numbers. We proved according to the proof outline shown in the original paper. We additionally need to prove the integrability of the program. But our proof requires a large number of steps of equational reasoning because we have not implemented proof automation. For instance, the equation about expected value spans 7 lines in pen and paper proof. But this part requires around 100 lines in Isabelle HOL. Let's move on to the next topic, formalization of PPV. The programming language of PPV is called HP-proc. Its type has the type of probability distribution, and its term has the Bernoulli distribution and Gauss distribution and monad operators return and bind. Typing rules are standard. We shallowly aimed PPV. That is, we implement PPV according to its semantics. In the semantics, types are interpreted as objects of QBS, where QBS is the category of quasi-Borel spaces. Objects are quasi-Borel spaces, and morphisms are structure-preserving functions. And typed term is interpreted as a morphism from its context to its type. In Isabelle HOL, we implement the typing context as follows according to its semantics. That is, E is a morphism from gamma to T. Similarly, logics of PPV are defined according to its semantics. In our mechanized PPV, programs are written in double-line index. That is, variables are distinguished by natural numbers. According to semantics, variables are projections. Thus, for instance, the first variable is referred to var1, and similarly, the second variable is referred to var2. The lambda abstraction is carrying according to its semantics. For example, this typing judgment is implemented in our mechanized PPV as follows. The first var1 is bound by the lambda, but the second var1 is the free variable. It is cumbersome to reason programs written in double-line index. And finally, we review the difference between the original PPV and our mechanized PPV. The first difference is about conditioning. Our mechanized PPV does not support the conditioning because we use the probability monad on QBS, while the original one uses the sigma finite measure monad on QBS. We use the probability monad because it is constructed from the Giry monad, and the Giry monad has been already formalized and included in the standard Isabelle library. And another important difference is integrability. We use those two equations in the proof of the Monte Carlo approximation. The first equation, called the linearity of expectation, holds if both f and g are non-negative, or both f and g are integrable with respect to d. The second equation is derived from the first equation. In the proof of the second equation, we use the first equation with functions which might be negative, and thus the notion of integrability is necessary. In the original paper, they implicitly assume the integrability and use these equations. Conclusion. We have formalized quasi-Borel spaces in Isabelle HOL, and also formalized a core part of PPV. And finally, we verify the Monte Carlo method on our mechanized PPV. The formalization of quasi-Borel spaces is available at Archive of Formal Proofs. The entire formalization is available at author's repository on GitHub. There are some future extensions of our mechanized PPV. The first one is conditioning. We need to formalize the sigma finite measure monad to support the conditioning operator. The second one is proof automation. We expect that it may reduce the cost of verification to prove simple equations semantically, rather than applying rules manually. The third extension is relational program logic. We have not implemented relational program logic, but we expect no major difficulties. There are some applications of relational program logic. For example, we can verify the sample size required in importance sampling. And the relational logic will be applied to differential privacy. That's all. Thank you.